then what happens is when I do plug it in, it works for a short time and then stops. It was brand new. These things are supposed to last a few years. I haven't been using it that much. Also, our next class, oh, let me remind you, by the way, that tomorrow the school is on a Friday schedule. So if you have Friday classes, you attend them tomorrow, but most of you don't. So if you have Wednesday classes, you have an extended vacation, which is how they used to do it years ago, which was a good idea the day before Thanksgiving. But anyway, so again, tomorrow is a Wednesday schedule, is a Friday schedule at school. Tomorrow, Wednesday, is a Friday schedule, so no Wednesday classes tomorrow. And so, okay, what I'm going to do about tests is this. We'll unite preparing for class tests with the final. Not the first day we're back, which will be a week from today, which will be December 1st, but a week from Thursday. So that's next week on Thursday. We'll have a test on the first half of the term's work, and I'll be explicit about that by email, even before we get together again. And then the following Tuesday, which would be 2 weeks from today, December 8th, we'll have a test on the second part of the term's work. And then the final is like almost a week and a half later. So our last class is December 8th, and the final is December 17th. So what's that, 9 days later? Not quite a week and a half. And that one will be comprehensive. Anyway, I'll get back to you by email. I expect to be able to get out the audio and video of oral out class meetings this term, and as well as some course documents that you haven't gotten yet, if things cooperate. So again, we'll have a test on the first half of the term's work, and I'll write to you by email. So check your email, not every minute, but over the weekend at some point. We'll have a test a week from Thursday, December 1st. No, December 3rd. December 3rd, that is. And then another December 8th. It's not ideal, but as I say, the whole situation isn't ideal. So if this works, I would like to prove that no polynomial in a single or multiple variables can be entirely prime representing, that you just get prime values. And so certainly it won't give all primes. It won't even give only primes. So, okay, let's do that. And then I'd like to go over some residual homework that we still haven't gone over. All right. Yeah. Okay, John. Yeah. All right. Well, let's go and hope for the best. So shut this off and get back on one note. Okay.
This meeting is being recorded.
Oh, okay, here we go. All right, just to verify, you can hear me, right?
Mm-hmm. Yes, Professor.
Good. Thank you. Oh, by the way, we talked about the power of powers and how 2 to the millionth power had more than 301,000 digits just to write the number. And then a simple computation with an elementary calculator gave the number of seconds since the universe began in the Big Bang, presumably 13.7 billion years ago. And that had 18 digits. And so if you take a look at 301 digits versus 18 digits, it would take to count up to the number that's represented in very compact form as 2 to the power 1 million. To count up to that, if you counted at one number per second, it would take about 12 times the length of the universe, the length of time the universe has existed. So you need 12 universes to count up to that number. By the way, actually notation, as I said, 2 to the millionth power is very, very compact. Writing it out in decimal form, meaning in base 2, would be, prohibitive. Just to write over 300,000, it's well over 250,000 digits. So notation makes a big difference. I once saw the multiplication of a 2-digit number by a 2-digit number, 23 by 47, something like that. Something that, I guess a fourth grader could easily do in very compact form. I once saw that written out in Roman numbers, and it took a whole page. So notation can actually be important. What I want to do a week from today is talk about congruence modulo n, and we'll see that notation that was due to Gauss is very powerful. Again, notation can make a big difference. All right, I'm about to, let me put some lines on the page for all the good that does. And now, all right, let's see if I can draw or write with this thing. So here goes theorem. Okay, it's not where, because I have it on. All right. Let's see how long this works. So again, we consider a constant to be a trivial example, but an example of a polynomial. Namely, it's the polynomial of degree 0, right? So the degree of a polynomial is the highest exponent that appears. So in a quadratic polynomial like ax squared plus bx plus c, that's said to be of degree 2, right? So a constant polynomial like f of x equals 5 is trivially always a prime, but a non-constant polynomial cannot assume exclusively, that means only this, cannot assume exclusively prime values. Okay, so we'll do it by contradiction. Suppose f of x, sometimes when you're talking about a polynomial, instead of calling it f of x, you call it p of x, but of course the symbol doesn't matter. I think the f of x notation was due to Euler, E-U-L-E-R. again, speaking of notation, it's a very useful notation because it allows you to distinguish. For instance, if you write y equals one function and y equals another function, that can be problematical. Sometimes you want it that way if you're graphing two functions together. But so that's one problem. You don't want to use the same symbol in the same context having different values. But also, even more important, as you know, whatever you put in for x in f of x, you have to put in for all the other x's, because when you use the same symbol multiply often in the same context, it has to have the same meaning. So we're going to do that. But first, let me remind you what a polynomial is. I think you know an nth degree polynomial. It's some coefficient a sub n times x to the nth plus a sub. So now I'm putting this in what's called descending order of powers of the variable. So the next lower power would be x to the n minus 1, and I'll just denote the coefficient of that power of x with the same subscript, and so on. So the next one would be a sub, we're going down, so it's n minus 2, x to the n minus 2, plus, and this keeps on going till you get down to a sub 2, x to the 2, plus a sub 1, x to the 1, plus a sub 0. Suppose that this has only prime values. Well, so far this is working. Okay, hope it continues. So for any x, f of x is a prime number, say p. So that whole polynomial equals p for any value of x that you put in. Well, let's put in let's replace x by, say, x prime plus m times p. That same p that we just had on the line above that. So it's a small p. So what will this give us? We'll have f of x prime plus mp equals a sub n minus 1, x prime plus mp to the nth, plus a sub n minus 1, x prime plus mp to the n minus 1. And so this will keep going. A sub 2, parentheses, x prime. Let's put that. Plus mp squared plus a sub 1, x prime plus mp plus, let's sneak that in there. Okay, so now let's observe that when the powers of what we have in the parentheses, x prime plus mp, we say are expanded, which means informally I'll put quotes around it, multiplied out, if you do the multiplication. Then every term in the expansion all right, expansions, except the first. Let's say something about that. If you remember the binomial theorem, you remember how you expand a binomial, and x prime plus mp is a binomial. But even if you don't know that, wait, this, in the line above, notice that first coefficient should just be a sub n, right? Yeah, a sub n. Yeah, that goes along with the x prime plus mp to the nth. Okay, okay, but even if you don't remember the binomial theorem, the binomial theorem isn't difficult. It gives coefficients that people who have had mathematics 3120 or 4120. You've seen the binomial coefficients in the probability of, well, when you have two possibilities, the probabilities use the binomial coefficients. But even without that, take a look at, for instance, suppose for instance you had, you don't have to really copy this, x plus a sub 1 times, well, why don't I just use what we actually have? Hey, look, suppose, look what's happening. Suppose we have our x prime plus mp squared. I'll just square it. So how do you do this? You square the first term. You take twice the product of the two terms, and then you square the last term. And notice that all terms except the first will have a factor of p. And then if you take what we just got here and multiply that by x prime plus mp again to get it to the third power, you would again, well, okay, look what I'm talking about. Maybe it's clear. X prime squared plus 2x prime mp plus m squared p squared. And then if you would bring it up to the third power, you'd have what? X prime plus mp again. And look what would happen. The first term times the first term would give you x prime to the third, but then all the other terms, then by this, it's just the distributive property. Look at the x prime here. When you multiply the second term here by x prime, you get AP. When you multiply the third term by x prime, you get a p. And certainly when you distribute this term into the other terms, you get p's. So what I'm saying is that every term except when you, in any one of these expansions, in the x prime plus mp to the nth, the next one, x prime plus mp to the n minus 1, all the way down to x prime plus mp squared, and then x prime plus mp. When you actually expand it, when you multiply it out, all terms except the first one. So, for instance, I'm going to get rid of this, okay? So, f of, what is it, 1, 2, 3, 3 lines up, this f of x prime plus mp equals, so it's a power of something with x prime in it. The expansion will have in the first, so here I'll write it, x prime plus mp to the nth. What's that going to look like? It's going to look like x prime to the nth plus so this is what I'm saying. When I say notice that when the powers of x prime it's kind of messy. When the powers of x prime in the polynomial, so you have powers of x prime plus mp, when those are expanded, you're going to get something like this. You're going to get, because you're multiplying it by it by it by it and so on, and by the distributive property, you're going to have an x prime times x prime plus x prime for each one of the factors of x prime plus mp. And so, yes, you will get x prime to the nth. But all the other terms, plus terms with p, all the other terms will have a factor of 3, of p. So look at what when we expand it, look at what f of x prime plus mp is. All right, so we have the first coefficient there, a sub n, and then when we raise the first term there to the power n, we're going to get x prime to the nth, and then there are going to be some terms with p in it. I'll get to that, and then the next in f of x prime plus mp, we have a sub n minus 1, and there we will have an x prime we'll have an x prime to the n minus 1. What I'm doing is I'm expanding f of x prime plus mp. So so from the first term that we get a sub n x prime to the nth, there it is on the last line, plus the next term is going to give us a sub n minus 1, here it is on the last line, times, then we're going to have the x prime to the n minus 1, there it is, and this will keep going. Let's jump down to where we have a sub 2 times, again, we have in parentheses x prime to the second, so that will give us x prime to the second, plus, as I just had but erased, terms with p in it, plus a sub 1 just plain x prime plus a sub 0. Now I'm going to amalgamate, I'm going to put together all the terms, look at this, that have factors of p. And I'll pull out a factor of p, and I'll just call this capital K times p, where, let's be explicit about what this is. I wasn't, so far this is holding up well. Before I was having a great deal of trouble with it. I cleaned using window cleaner. I cleaned the screen, and with just some plain soap, I cleaned the pen point, the Apple Pencil point. I don't know whether that made a difference. So far it's working nicely, as it should. So where KP is simply the sum of all the other terms again, each of which has a factor of p. Right, so again, when we expand any of these x prime plus mp to a power, you'll get x prime to that power, but all the other terms will have factors of p. And so I'll just put those all together as kp. Okay, but remember that up here where it says proof, under theorem, proof, suppose that this polynomial equals p. So suppose that so this shows that I'm not going to rewrite that whole thing. Okay, so okay, so where it says thus, f of x prime plus mp equals that, and that whole polynomial is f of x prime plus p, and so it's divisible by p. That is, p divides f of x prime plus mp. And so we're assuming that f of x prime plus mp is prime. So that's where it says proof. Suppose that this is prime generating, so it actually equals p. Well, I'll go to the next line. So I asked you to think about this on Thursday. If a prime number divides a number which is a prime, and we're supposing that f of x prime plus mp is a prime, if it's divisible by p, okay, if that's a prime number, it doesn't have a lot of divisors. One divisor is p. P divides it, as we just saw. P divides f of x prime plus mp. But p is not 1 because it's a prime. So f of x prime plus mp, which is divisible by p, but we're assuming that f of any x, such as x prime plus mp, is a prime number. Well, and its only non-1 divisor is p, so it itself must equal p, because it's divisible only by itself. Well, if it's divisible by p, then p is itself. It's divisible by p, and it's not, since it's a prime, supposedly, it's not divisible by anything other than itself. So what divides it is it itself. So I had no restriction on m. I mean, other than that it's an integer, but that's fine. Oh, well, we have a little problem there. Remember how we discussed the fact that a polynomial of degree n can't have more than n solutions or n roots? Or if you look at the first formulation, f of x prime plus mp has, saying the same thing, more than n zeros, if you want to put it that way. How so? Well, one for each value of m. It's a contradiction. A polynomial of degree n can't have more than n zeros. Or if you're looking at it as f of x prime plus mp equals p, which is the same thing, the equation f of x prime plus mp equals p can't have more than n solutions. And it's the same thing, saying that that equation can't have, if you put the p on the right side, then you have the equation f of x prime plus mp equals p. And so then you can say that equation can't have more than n solutions. Or if you subtract the p, then you get a polynomial of degree n, and that can't have more than n zeros, or sometimes called n roots. Well, let's see, where did that come from? Oh, look at where it says proof at the top. It says suppose. Suppose that that polynomial has only prime values. Well, we got to a contradiction down here. And so we conclude that the supposition at the top that the polynomial f of x has only prime values is incorrect. A polynomial we say polynomial in x, that means that's the variable, can't represent only prime numbers. And what I mean by represent is what I said at the beginning. It can't generate prime values only when you put in different values of x.
Professor?
Yep.
Could you explain the part where you said f of x prime plus mp is divisible by p?
Yeah, because, yeah, exactly. Yeah, because, so where it says thus f of x prime plus mp equals, so when you multiply it out, when you expand the powers of x prime plus mp, the first term of each of the expansions has an x prime to whatever power you're up to. When you're doing the first term, so you have so each of those, when you expand them, has the first term, x prime, to the corresponding power. So there it is, x prime to the nth. That's for the first term up here. Here we have x prime to the n minus 1. We get that when we expand the second term here. See, we have an x prime to the n minus 1. There it is, x prime to the n minus 1. And this keeps on going. Down here at the end, we have x prime plus mp squared. When we do the squaring, we get our x prime squared, and then we just have an x prime. And all the other terms.
Are those individual terms divisible by p?
No. Oh, no, but we're assuming that the
Oh, I see. I get it now.
Yeah, we're assuming that when you put in any number for x, such as x prime, we always get a prime number, say p. So, and then all the other terms have factors of p. And so the whole polynomial, the original polynomial, this equals p. And then this term, so this equals, I guess it would have been clearer if I had put in over here that what this shows is that f of, I'm sorry, it's to the right a little bit, f of x prime plus mp equals p plus kp. And then you can take out that common factor of p and write, you don't really have to do this separately, f of x prime plus mp equals p times 1 plus k. And that is the definition, going back to the definition of divisibility. If something such as f of x prime plus mp equals p times something, that's a definition of p divides f of x prime plus mp, which is what we have here. So yeah, f of x prime plus mp equals the original polynomial, which supposedly is always a prime, call it p, and then the other terms have that same p in it. So we're saying that where it says suppose that polynomial always has a prime value. And suppose that when you replace x here, when you replace x by x prime, you get the polynomial p. And then you have terms with p in it when you evaluate f of x prime plus mp. So it equals what it shows it's being equal to. And so p divides f of x prime plus mp, and that will lead to a polynomial with more than a polynomial degree n with more than n zeros, and that's not permissible. As we showed last week. And so a polynomial with more than one variable and I pointed out that you've dealt with functions of more than one variable when you were when you work with partial derivatives in free space, or in mathematics 4100, you can deal with even more. That a polynomial in more than one variable cannot assume only values. Suppose we have f of x sub 1, x sub 2, x sub 3. Suppose we have a polynomial in, and I'll give a specific example if this is sort of too abstract, if you don't know really what this means.
Professor?
Yeah.
What's that underlined word, like the second last line? That underlined word.
Oh,
like
corollary.
Corollary. Okay.
So remember, a corollary is a theorem that follows easily from another theorem. So the hierarchy is you have a main theorem, and coming before a main theorem is a lemma, which leads up to it and facilitates it. And you often use a lemma when a theorem is going to be complicated or sort of have, you use lemmas when you're breaking a big theorem into more manageable parts so that it's easier to see the main drift, the idea of proving the theorem without sort of going out onto tangents. I mean, necessary tangents, but that would sort of interfere with the flow of the theorem. So you prove one or more lemmas before that. And then after a main theorem, it frequently happens that you can apply it to specific cases without going through the whole proof again. So as you'll see in a moment, like in one step on the basis of that theorem, we can prove that if you have a polynomial, and I'll give an example. Maybe I should have started with an example, but I'll give it in a moment. So And I'm contending that it cannot assume only prime values for all values of the variables. Maybe washing this did remove something. I may have been taking extremely good care of this pen, but well, maybe it has some residue on it or something, because it's working nicely now. So it cannot assume only prime values for all values of the variables, because if we give specific values, so again, this f of x sub 1, x sub 2, x sub 3, up to x sub n, so that's a function of n variables, a polynomial in n variables, but let's see whether that can always represent a prime number for all values of the variables. Well, suppose it gives specific values to the x sub 2, x sub 3, up to x sub n, then look, if we give specific values 2 or 4, all but the first one, so we get what I just wrote here, we have a polynomial look at it. So when the other variables have specific values, and again, if this is going to represent a prime for all values of the variables, well, then when, n minus one of them have specific values, it's supposed to still always give a prime number. But no, when you do that, then you're left with a polynomial in just one variable, x sub 1, and the theorem says that a polynomial in one variable means it has one variable in it. One variable cannot always be a prime. So that's why you can't have a polynomial in more than one variable, because then that always gives primes for all values of the variables, because then you can just assign specific values for all but one of them, and then you're left with a polynomial with just one variable, which should then represent only primes, but the theorem says that doesn't happen. So, but I said I'd give an example. Suppose f of, instead of x sub 1, x sub 2, I'll write x comma y. So this is a polynomial in two variables, x and y. For instance, just make up something. There. But if we choose a value for one of them, then we get a polynomial in the single variable x. So it would be if y equals 1, 3x to the fourth minus x plus 5x to the sixth minus 8. So that's what I'm talking about. When I say if you have a polynomial, or any function, but I'm talking about polynomials, a polynomial in more than one variable, if you assign specific values to all but one of the variables, then you're left with a polynomial in one variable, and we know that can't assume only prime values, and so the original function couldn't assume prime values for all values of, in this case, x and y. Okay, let me leave the new work at that and go to so we still have some on mathematical induction, but we never went over any of the questions in unique factorization. So that's on the sheet that you have with the Diophantine equations at the top, and then a design that I was able to put onto it, and then unique factorization. So unique factorization is the fundamental theorem of arithmetic that provides that every number, every composite number it can be factored uniquely into primes, except for the order of the primes, that the primes themselves are the same, unique. You can't do it another way. Okay, so let's see whether we can. So what I designate is one, prove that if n is a square, that means a perfect square, Prove that if n is a perfect square, the square of an integer, then each exponent in its prime power decomposition is even. So decomposition means you're decomposing it or breaking it down into prime factors. Well, so if n is a perfect square, suppose, I'm not going to write all this because I want to try to do all 5 of these questions. So how would this look? So n squared equals n times n. Again, that's what a perfect square is. It's the square of an integer equals, and suppose the prime power decomposition is, I'll just do it to the first power and then we'll see why it has to be squared, but you'll see easily that the powers don't have to be 1. So suppose n, according to the fundamental theorem of arithmetic, breaks into, say, p sub 1 times p sub 2 times p sub, I'll use p sub r. I don't want to use p sub n because I'm calling the number n, so that would be confusing. And again, that's the only way to do it. So again, now I'm factoring the other n into primes, the second n into primes, but these primes have to be the same as the first set of primes because it's the same number and you have unique factorization. So p sub 1, p sub 2, etc., through p sub r. And again, if any of those had exponents, it doesn't matter because you're going to be multiplying it by itself and it'll become even. So the way I have it here is this will give p sub 1 squared, right? P sub 1 times p sub 1 times, then we have p sub 2 times p sub 2, which is p sub 2 squared. And you keep on doing this, and finally you get to p sub r in the first parentheses times p sub r in the second parentheses. And so we have that. Question 2. Prove that conversely, the number represents, what I mean by it represents, it equals. Okay, so suppose each exponent is even, so suppose, say p sub 1, which is being squared, or any other even number, times p sub 2, which is being squared, times p sub r, which is being squared. Well, notice that that can be written as, by the generalized associative property of multiplication, that can be written as p sub 1 squared. It would be p sub 1 times p sub 1 times, then we have p sub 2 squared. And so I can associate it this way, p sub 2 there and p sub 2 there. And similarly, since all the exponents are even, we have the same number of them appearing twice. That's what squaring means. So we have, I'll put the p sub r there and p sub r there. But by unique factorization, in each of these parentheses, p sub 1, p sub 2, dot, 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 times p sub r, and so on, is some number n. I'll put it on the next line. So that equals whatever that number is, but those are the same factors. So it's n again, which is n squared. Is a perfect square. In question 3, actually we went over question 3 once. Let's find the smallest integer that's divisible by 2 and 3. And those are primes. So by unique factorization, they have to be present in the product of primes for the number we're looking for. And since we want it to be the smallest, we want to include nothing else. We want to keep it as small as possible. And the number we're looking for has to be both a perfect square and a perfect fifth power. Again, a perfect fifth power is a number like 32, which is the fifth power of an integer. And so to be a square and also to be a fifth power, so it certainly has to be a fifth power. How about a sixth power? No, that's not a fifth power. You'd have to go up to the 10th power, but the 10th power is also a perfect square, right? What's the 10th power the square of? It's the square of the fifth power, right? Something to the fifth power to the second power is to the power 10. And so we saw that that was 2 to the 10th times 3 to the 10th, or 2 times 3 to the 10th. And again, you read this as which equals, not just equals 6 to the 10th. All right, so we've looked at that one before, and it's already like 10 after 7. So let's conclude with the others. So is it possible for a prime p to divide? So can a prime p divide both n and n plus 1, where n, and hence n plus 1 is at least 1. Well, let's say, suppose it can. Suppose a prime p can divide both n and n plus 1. So let me write this more explicitly. Suppose it can. So suppose p divides n and p divides n plus 1 so that n equals p times k and n plus 1 equals p times j. Okay, that's what it means to say p divides n. It means n equals p times something. And to say p divides n plus 1 means that n plus 1 is p times something. So suppose we write equals, on one hand, n plus 1 minus n equals 1. But on the other hand, if n plus 1 equals p times j minus n is p times k, which equals p times j minus k, which equals p times, say, m. So on the one hand, if p divides both n plus 1 and n, we find that this n, I'll put it in parentheses, this n plus 1 minus n equals 1, but it also equals p times m. You see why that's a contradiction? P being a prime number is more than 1. So P cannot divide 1. Look at this last equation there. 1 equals P times M. No, we proved earlier in the term that a divisor of a positive integer must be less than or equal to that integer. So this says P divides 1. No, a prime, that would be at least 2. No, 2 doesn't divide 1. No higher prime divides 1. So conclude that two consecutive integers n and n plus 1 cannot have a common, that means the same for both of them, prime divisor. And so let's conclude today with the last of these questions. Prove that n times n plus 1 is never a perfect square for n. There is a positive integral n for n greater than positive integer, okay, greater than or equal to 1. Okay, so we just showed in question 4 above that n and n plus 1 do not share any prime factor in the prime factorization. So n equals, say, p sub 1, p sub 2, say p sub r, and n plus 1 equals q sub 1, q sub 2, up to say q sub t. So if n times n plus 1 is a perfect square, we proved in question 1 that the exponents in the prime decomposition of n times n plus 1 are even. So n times n plus 1, so it's n whose prime decomposition are p sub 1, leave a little room, p sub 2, leave a little room, up to p sub r, leave a little room. And then the n plus 1 has different prime factors. Q sub 1, leave a little room. Q sub 2, leave a little room. Up to Q sub t, leave a little room. But from question 1, we saw that if this n plus n times n plus 1 is a perfect square, all these exponents have to be even, could be 2 or any other even number. So, and so, so we showed in question 2 that if each exponent is even, then that number is a perfect square, showing that since the exponents in the prime decompositions of n and n plus 1 are even, both n and n plus 1 are themselves perfect squares, right? And number 2, if each exponent is even, then the number has to be a perfect square. So we showed that in question 2. But no two consecutive integers above 0, and it is above 0. It says it's never a perfect square for n greater than or equal to 1, or as I guess I put it, positive integral n. Above 0 are perfect squares. Because what are the perfect squares? Well, if you start with 0, so 0 and 1 are the only two consecutive numbers that are both perfect squares, but we've excluded 0. But after that, the next perfect square is not 2. 2 is not a perfect square. You have to go to 4. Well, the number next, right after 4, if n is 4, n plus 1 is 5. No, that's not a perfect square. No, you have to jump to 9. After that, 16, 25. And I don't know if you've ever noticed this, but let's take a look at the differences of the squares. So starting with 0, 0 squared is 0, 1 squared is 1, 2 squared is 4, 4 squared, 3 squared is 9, 4 squared is 16, 5 squared is 25. And if we take a look at the differences, the difference there is 1. Then we have to jump up from 1 to 4 is 3. Then the difference from 4 to 9 is 5. Then the difference from 9 to 16 is 7. And the distance, or the difference between the distance from 16 to 25 is 9. And so we see that the differences of consecutive non-negative perfect squares make this plural. The differences of consecutive non-negative squares forms the sequence of odd numbers. So no, you can't have two consecutive positive numbers that are both perfect squares. How could you see this? Well, it's very simple. Let's take a look at the difference of the squares of two consecutive numbers. So this is n squared plus 2n plus 1 minus n squared. Yep, it equals 2n plus 1, which is an odd number. And so n equals 0, 1, 2, 3, etc. generates the sequence. Sequence is a list in order, as you know. Sequence of odd integers. Oh, by the way, okay, so we'll leave it at that. So that covers that homework. Let me come back to you and say a few concluding things as we are for the week. Okay. I have a former student from, some of you actually may know her. She's in my class a number of times. She majored in mathematics, and she's preparing to take the GMAT tests. And she asked me a question. The question was from the GMAT, how did this go? If you form the product of even integers from 2 to 100, what is the smallest, what would be the size of the smallest prime factor in that product? The product of all the even numbers from, well, 2, one's not an even number, from 2 to 100 inclusive. Where would you find the smallest prime factor? And then they gave ranges, 1 to 10, 10 to 20, 20 to 30, 30 to 40, or more than 40. We have actually done something, plus 1. Not just the product of all the even numbers from 2 to 100, the product of all the even numbers, 2 times 4 times 6 times 8 times 100 plus 1. I'll leave that for you to entertain yourself with if you want to. We've actually done something in this class that will allow you to determine the answer to that, about how large the smallest prime factor of the product of the even positive numbers from 2 to 100 inclusive plus 1. Where would you find, how big would you have to, how big would the smallest prime factor of that product plus 1, that might remind you of something, give you a clue as to what to do. Would it be a number between 1 and 10, the smallest prime factor, or 10 to 20, 20 to 30, 30 to 40, or more than 40? Anyway, so we will get together again a week from today. Well before then, I hope to have all the class, again, I don't like the word lectures, lessons, available to you, and also class documents. And I'm actually on the verge of being able to, I can give you a test, I can get the test back from you, but I would like to actually be able to mark it and send it back to you, rather than just giving you a grade and then putting some notes on it about where you may have made a mistake. That's the part that I'm not sure of yet. It does involve forming a PDF, and I think most of you can do that. We should have a test, make sure it's working before an actual test. So we'll get to that. Meanwhile, I suppose that if you and or your family are doing anything for Thanksgiving, that's already set and settled and not subject to change. But it's deemed wise to forego what might be a traditional Thanksgiving, family gathering, in favor of enhancing the prospects that we'll still be here for next Thanksgiving. So the other possibility that I heard actually on the radio, which is a kind of neat idea, don't cancel Thanksgiving this year, but postpone it. Decide that you'll have Thanksgiving get together in July or something like that. In any case, however you do it, take care. And also, at the risk of sounding a little corny, this holiday is Thanksgiving. And for all the deficits in life these days and how things, you might wish they were better, but there's still some bright spots, I trust, in your life. I hope everyone is coping at least adequately. And I think it's psychologically healthful and also true to realize that we probably all have something to be thankful for. If you don't like the word thankful, grateful for. And it doesn't have to be grateful to anything specific. It can include families who have supported you in doing what you're doing now, going to school, spending the time, going through all this, or whoever it is, a girlfriend, a boyfriend, a parent, a grandparent, or a good friend of any sort, a pet. Look for things to be grateful for on this occasion. And with that, I hope you find things to be grateful for, and that in time, things will work out better. So, yeah. Well, yes, I want to get, I want to give you the notes and be explicit, hopefully over the weekend, as to what the topics will be. I also want to send you the curriculum. And so we started with some just a talk, which won't be on a test. I have here the nature, history, and ramification of the theory of numbers, solved and outstanding. Outstanding means not solved. Problems in number theory. Okay, not that. But then we talked about but I'll send this to you. The integers as an ordered integral domain, absolute value, properties of inequalities, divisibility, what that means, the division algorithm, how we can use the division algorithm to distinguish between even and odd numbers, depending on whether the remainder in the division algorithm is 0 or 1. And the principle of mathematical induction, that'll be there. The sheet on forms of integers, we went over most of that, although not all of it. divisibility and other characteristics of integers having a given form, the greatest integer function, the bracket function, which we've used. What I have here listed as 4 is proofs by mathematical induction and recursive definitions. Remember, we define, say, n times a recursively by defining 1 times a to be a, and then saying, okay, then n plus 1 times a will be na plus 1 more a. That's a recursive definition or an inductive definition. And then the well ordering of the positive integers. Any non-empty set of positive integers has a least element. And then we used that idea when we studied common divisors and the idea that a linear combination of 2 non-zero numbers is the greatest common divisor of the 2 non-zero numbers. Remember what greatest common divisor means? It means it's a common divisor, and anything that divides it divides the original 2 numbers. Greatest common divisor, and there we use the well ordering of the natural numbers, that is, that any non-empty set has a least element. And we spoke about prime and composite numbers, and we proved that if a prime divides a product, it divides one of the factors, and if in fact any number divides a product and it's prime to one of the factors, it divides the other. Then we studied Diophantine equations, and again, I'll send this to you. How to solve Diophantine equations, how to get all solutions, then how to get solutions subject to certain conditions, like they have to be positive. Then we looked at Euclid's proof of the infinitude of primes, and we talked about the distribution of primes. We showed that you can find arbitrarily long sequences of consecutive prime-free numbers, all composites. Remember how we did that? Like 1,000 factorial plus 2, 1,000 factorial plus 3, 1,000 factorial plus 4. None of those is going to be a prime number because you have a common factor between the 2 terms. Then we also use the Sieve of Eratosthenes to determine whether a given number is prime or not. All you have to do is test the primes whose squares do not exceed the number. And if that number is not divisible by any prime number, so you just have to test the prime numbers whose squares do not exceed the number in question. So for instance, one of the examples we had, as I recall, was determining whether 47 is a perfect square. So you just have to see whether it's divisible by any of the primes whose squares do not exceed 47. Well, 7 is too big already because its square is more than 47. So you just have to look at, you have to see whether 47 is divisible by 2. No, it's an odd number. Is divisible by 3? No, 48 is. 47 isn't divisible by 5, and that's it. So by testing 3 numbers, you determine whether 47 is a prime number or not. That's the Sieve of Eratosthenes. Then we did what we were just going over, unique factorization and the fundamental theorem of arithmetic. And then we talked about how you can write numbers in different bases and the uniqueness of the representation. Now, I'm not going to ask you to prove any of these long theorems, especially with a bunch of subscripts that you can easily get lost in, but you certainly have to know the concept, or I might start you on a proof and ask you what the next step would be, and then actually use some of these things. And then, of course, we had the number of digits using the greatest integer function, the logarithm of the greatest integer and the logarithm of the number over the logarithm of the base. That plus 1 gives the number of digits in a given number. And then we had the Euclidean algorithm for actually finding the greatest common divisor. So that involved repeated uses of the division algorithm. And then what we did today, and on Tuesday, that is that the polynomial can't represent exclusively prime numbers. Then on Tuesday, which I guess will be our last teaching day, I would like to bring in something I mentioned at the beginning today, namely equivalence relations. Well, we've talked about equivalence relations, but not formally. We'll make it a little more formal, and then at least get to the definition of congruence modulo n, and then prove a couple of the elementary theorems, show ways in which congruence modulo n differs from standard algebra. And if we have time, see how to find remainders when you divide by large numbers. Wish we had a little more time, but again, I think everyone is going more slowly with this kind of instruction than in class. But again, doing our best, and our best is maybe by definition good enough. Well, I mean, I assume you've been taking notes and doing the homework and going through it. I mean, as an adjunct to it, since we have this, we have the deficit of this, but we also have, I suppose, an advantage of being able to go over the lessons. But I assume you've been coming to class, and I think you have, Andrew, if I remember correctly, you may have a perfect attendance record. Many of you seem to have been doing so. And yeah, I mean, I expect that you've been following what we're doing and doing the homework. And the idea of the two tests is that will basically prepare you for the final. If you prepare for each of those tests, and they'll be several days apart, you'll be ready for the final. The final and the class tests will be taken straight from what we've done in our class sessions. Nothing else, no outside reading. It'll be straight from there. And again, I'll just go through the topics and make up a question or two on each subject that we've had. No, I think that at least will give us 3 substantial tests, which is reasonable for grading. I mean, it's true that frequently in graduate classes, they'll sometimes give only one final at the end of the term, sometimes even one final at the end of the year. But then there's too much riding on a single test. So this way, the 2 tests are spaced, 5 days apart, and you do have some time now. I think most of you will have 5 days off because I don't think you have classes on Friday. That should provide time to not to learn it. If you've done nothing all term, it's too late. You're not going to study. You can't cram mathematics. But if you've been attending class and following along, reasonably well, you're not expected to be an expert and know everything. You just have to know enough. So, as I promised at the beginning of the term, tests will be a reasonable investigation into what we've done. Nothing else. No, there shouldn't be any surprises on the test. And as I say, preparing for those 2 tests, which are almost a week apart, and you have over a week now to prepare for the first of them, and then another 5 days, and that should not be overly arduous. I mean, there's always a crunch at the end of the term. That's inescapable. Personally, I'm not really in favor of having finals in every course that you take, but that's not going to change. What we are hoping for, okay, so they've made one major change now, which is permanent. You have till the last day of classes to get out of a class with a non-penalty grade of W. I've always been in favor of that. Used to be only after 11 weeks. The other thing that there's some talk about, which I'm in favor of, is doing away with grades of F and just giving everyone a chance to take a class for P passing or NC no credit. That's enough of a penalty. You've wasted time, money, effort. I don't know. This term they are definitely not doing that. And this comes down from the university and not the college and not the class. But I am hoping that that they will make permanent the idea of giving you the opportunity to get a grade of P or NC for no credit. Or, if you're running an A or a B, go ahead and take the A or B. But if you're not, at least, you've got a passing grade. But again, I have nothing to say about that. So I will probably get the, because I think it's working now. I would have before today. What I've been doing is going over all the lessons and making sure that there are no slip-ups, that there are no, as much as possible, no illegible things that I've written, because this tablet is so slippery, it's hard to write properly, even with the lines. And then this wasn't working. I don't know why it's working now, maybe because I actually cleaned the end of it. And I know how to get it out to you. So the way will be, and I'll write to you as emails, so you don't have to remember this, but I'm going to get all the classes that we've had, except the first, like when we just talked about it and I had the whiteboard and I couldn't save it, onto documents in Blackboard. That's where it'll be. And maybe some of the class documents like this also there, but I'll email you. And as I say, I also want to set up a test to make sure that I get it out to you and you can get it back to me. So we'll do that next week, or
Professor,
possibly before then. Yeah.
what will the format of the exam be?
Because I've spent all my time trying to get through these lessons, I haven't actually composed a test, but it will be during the class period, and I'll give you some extra time to make PDFs and upload it to send it back to me, but it will be timed, and it's much more difficult to give a test this way than in class. So in class, there would tend to be maybe some computational questions, but since you can get all of that online on the internet, which is part of the reason it's going to be timed. Usually in a regular class, I don't care how long you take, but I don't want you to have time to start, doing research on the internet. So I have to figure out ways to, and I think I have some ideas, I once mentioned this, to start you on a proof. So you would have to follow along with the proof that I've already started, and that would preclude the possibility of going online and just downloading a proof. The other guarantee against that is I will read carefully how you write your proofs, and I will probably be able to tell, and there are really serious consequences that we keep getting information about. Should probably tell you about it. By starting you on a proof and having you fill in the next step or next few steps or whatever it is, you won't be able to just download anything you get online. You'll have to follow along with what I'm doing, and it'll have to be, I'll probably be able to tell whether it's your work, whether it's your writing or not. If ultimately there's any question about, and I'll compare what people wrote, and it would not be a good idea to engage in academic dishonesty. If there is any question, I would